Hello everyone. In our today's session, I have brought a new topic for you, that is the limitation of Bohr model. In our previous lecture, I have explained all the related points of Bohr model. So I think you all have got properly. So let's discuss all the limitations in detail. So the first limitation which I am going to discuss with you, that is Bohr was not able to explain the finer detail of the hydrogen atom spectrum. It means he was not able to explain fine spectrum of hydrogen atom. That was the first limitation of Bohr's. Okay. Now the second limitation, as I have written, it was unable to explain splitting of spectral line in the presence of magnetic field as well as in the electric field. It means he was not able to explain the Zeeman effect and the Stark effect, that we call it the splitting of spectral line in a magnetic field. That phenomena is Zeeman effect, and the splitting of spectral line in electric field, we call it, this is the Stark effect. So Stark and the Zeeman effect were not explained by the Bohr's model. Now the next limitation, it could not explain the ability of atom to form the molecule by the chemical bond and the shapes of molecule. It means he was not able to explain the formation of molecule, and their shapes and symmetry were also not explained by the Bohr. And the next limitation was he was not able to explain the three-dimensional structure of an atom. And the last one is that the de Broglie's and Heisenberg uncertainty principle, that was also not explained by the Bohr model. So here I am picking the point of de Broglie's equation. So de Broglie's equation, that relates with the dual behavior of matter, that we have to understand, and after that I will explain the de Broglie's equation. So here, as I have written, de Broglie, that was a name of scientist, he proposed that matter like radiation should also show dual behavior, that both particle and the wave like properties. Here I mean to say, whenever that it is in a stationary position, that it will behave as a particle, but when it acquires a velocity, then it behaves as a wave. Okay, when acquires the velocity, it behaves as a wave, and when it is in the stable position, it behaves as a particle. So this is it's a dual behavior. Okay, so as electron and photons has momentum as well as the wavelength, so the wave associated with the particle in motion is called a matter wave or the de Broglie wave. So here I will tell you what is the de Broglie equation. Now you see here, as we have studied the Planck quantum theory, so according to the Planck quantum theory, we get it E is equals to h nu, that we consider this is the equation 1. And according to the Einstein equation, that we call it E is equals to mc square, this is the equation 2. Okay, so as both are the form of energy, so we are equating both of them. So E is equals to h nu is equals to mc square. So we will get it here. Now if you will find out, h is equals to mc square upon nu. As we know that nu is equals to c upon lambda. So in place of nu, you can write there m c square upon c upon lambda. In place of nu you are writing. So h is equals to, it becomes c to c will be cancelled. So we will get there mc into lambda. So as we have to find out lambda, so lambda, that can be written h upon mc. As we know that c is the speed of light, so that can be considered as a velocity. So in place of c, if you are writing there v, so that becomes lambda is equals to h upon mv. So this is the de Broglie's equation, that is to be used to find out the wavelength of the matter wave. There is a one more thing, as we know that mv, this is the momentum, so that can be denoted by the p. if h we are considering as a constant, and as we know that this is a Planck constant, so lambda it becomes inversely proportional to the momentum. Okay, I hope you all have got it. So here we have to understand what are the significance of de Broglie's equation. So the first significance, de Broglie's equation is applicable to all material objects but significant only in case of microscopic particle. So as we have to study the nature of microscopic particle, then this de Broglie equation can be used, but it cannot be applicable for macroscopic particle. So de Broglie's relationship has no significance in our daily life. Okay, so that we must know that. Let's discuss about some numerical problem which relates to the de Broglie's equation. So the first numerical, what will be the wavelength of a ball of mass 0.1 kg moving with the velocity of 10 meter per second. So here the velocity is given v and mass is given. You have to find out the wavelength. So again use there the formula lambda is equals to h upon mv. Okay, let's see the next numerical which you have to solve. The mass of an electron is 9.1 into 10 to the power minus 31 kg. If its kinetic energy is 3 into 10 raised to the power minus 25 joule, calculate its wavelength. So as you know that as you have to calculate the wavelength, you have to use the formula lambda is equals to h upon mv. Here mass is given but velocity is not given. So for finding velocity, you have to use the term of kinetic energy. Kinetic energy is given. So kinetic energy is equals to half mv square, as we know that. So kinetic energy you put here, you mass already given in the question, you will be able to calculate the value of v. When you will get there the value of v, you have to put in this formula and calculate the wavelength. I hope you all have got it how to solve this question. In the same manner, I have given these two questions. Calculate the mass of a photon with a wavelength 3.6 angstrom. You have to convert into meter or in the nanometer. Then you have to find out the wavelength. Same formula you have to use here. And next is to be the velocity of the electron in Bohr's first orbit and is 2.19 into 10 to the power 6 meter per second. It means the velocity v is given. Okay, and calculate the de Broglie's wavelength. Mass will remain same of electron as I taught you in the starting of the chapter. That mass of electron you have to take. I hope you all have got it. Okay, try to solve all the numerical problems at home. That's all for today.